This is the first part of a four-part series where we're going to look at derivatives and the shapes of curves. So we're going to start by defining some shapes. The first one is something we've talked about before, and that is when a curve is concave up. So as a reminder, concave up looks like this. We said it looks like a U shape where it has that happy face shape, and this is concaved up. We saw before that something is concave up when the derivative is increasing. So you can say when the first derivative, so f prime, is increasing. And that is also going to mean that f double prime, so the second derivative, is greater than 0. You can say a curve is concave down, so that's the frowny face. It looks like a little mountain. When the reverse is true, so that would be when the first derivative is decreasing, which would mean that the second derivative would be less than 0. Now we have an inflection point, and that is where the concavity changes. So maybe it's concave up and it switches to concave down. So right here, where the concavity changes, that would be our inflection point. So an inflection point correlates to the change of concavity. And that is going to mean that our second derivative is going to equal 0. Now in the image here I have a concave up switching to concave down. It could also be the other way. It could be concave down switching to concave up. But the concavity is going to change, and that's where we'll have our inflection point. So here we're going to look at some different pieces of the graph and see what information we can extract. So in question 1, it says use the given graph of f. So this is of f. So this is just our original function f to find the following. So in part A, we are looking for the intervals where f is increasing. So if f is increasing, that means that we have a positive slope. It's like you're riding up the ski lift. You are increasing as you go. So if we look across here, it looks like from 0, if we trace across, we're increasing, 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 increasing. It looks like we're increasing all the way until 6. So for this first one here, starting at 0, going to 6, we are increasing. But then it looks like we begin to decrease until we get here to 8. It looks like from 8 until 9, we're increasing again. So these would be our intervals of increase. And if we look for the next part, I'll put it down here so it's with our question. Now we're looking for our intervals of decrease. So if we're looking for where it is decreasing, we're looking for where it is going down. So if we start right here and we look at this part of our graph, it is decreasing. So that would be our interval from 6 through 8. Now it's asking us where the original function f is concave up. So let's get rid of these so we can see it a little bit more clearly. Okay, so that dot doesn't want to erase, we'll just leave it be. So we're looking for where f is concave up. So if we're looking for concave up, that means we're looking for the happy face, the smile, like we have in the top here. So it looks like it's concave up right here. It looks like it's going to switch to down, looks like it's concave down, switches right here, and it looks like it's concave up again. So it looks like we have these two intervals where it's concaved up. So that looks like it correlates from x being 2 through x being 4. So that would be our first interval. And then again from 7 to 9. being our second interval. And we use the open parenthesis because, again, those points, remember, those are the critical points where something's happening and something's changing. And then for the next part, for part D, it's asking us the intervals where f is concave down. So it looks like it's concave down right here from 0 to 2. And then again from right here at 4, and then over to 7. There we go. For the next question in part E, it's asking us for the inflection points. Now it's asking us for the coordinates. It's not just asking us for the x value, it's asking us for the coordinates. So we need the x and the y. But we can figure this out. So if we look over here, we've already dotted them. We have one right here at x equals 2. We have one right here at x equals 4. We have one right here at x equals 7. Now we need to see if we can figure out the coordinates. So 2 looks like 2 goes with 3. That one's not so bad. It looks like 4. We're going to have to eyeball that one. I'm going to call it 4.5. We don't have the exact function. So right here, we just have to do the best that we can. I'm going to call that 4.5. And 7 looks pretty good. Looks like it aligns to 4. So these would be the coordinates for the points of inflection. So let's see if we can use all this and solve question 2. Question 2 is asking us to use the first derivative test to find the local maximum and minimum values of this function. So the first derivative test, what that means is we are going to figure out intervals where something is happening on our curve. Then we're going to figure out the sign of the first derivative. And by sign, I mean, is it going to give us a positive number or a negative number? And that's going to tell us if it is an area of increase or an area of decrease. So in order to figure this out, what we need to do first is we need to find our first derivative. So here we have our equation, y equals 3x squared minus 12x plus 4. So if we take the derivative of that, we get the first derivative is equal to 6x minus 12. So remember, you bring down your power, so 3 times 2 is what gives us 6. And then you subtract 1 from the exponent. So 2 minus 1, that's what's going to give us x to the first power. So 6x minus 12, that's going to be our derivative. We know something happens when we have our first derivative equaling to 0. Remember, that's what gives us our max or our min. That's where we change from increasing to decreasing. So let's see where that is. So let's say 0 equals 6x minus 12. If we solve this down, we can add 12 to both sides, which will give us 12 equaling 6x. Divide both sides by our 6, and we get x is equaling to 2. So that means something happens at 2. Well, if something happens at 2, then that means 2 right here is going to break apart our intervals. 2 is going to become our critical number, and that's what's going to separate our different intervals. So if we look at this, we'll have one interval from negative infinity up to 2, and then we have our critical number of 2, and something's happening at 2. We have to figure out what. And then we have the rest of the real number line. So 2 through infinity. So this is broken into 2 intervals, and we know it's broken into 2 intervals because we had one critical value here. If we were able to solve this for multiple critical values, we would have had multiple intervals to consider. But in this case, there's only one place where the derivative could equal 0, and that's at 2. So the only division for our intervals is at 2. Now we need to figure out the sign. So we need to be very careful. This is the first derivative. We're looking at the sign of the first derivative. So that means that we need to consider the first derivative. So what you do is you look for any point that is in your interval and you look at your first derivative to see what the sign is. It doesn't matter what the value is, like 1, 2, 7, 12. It matters what the sign is. So let me show you what I mean. Within our negative infinity to 2, we have the value of 0. X equals 0 is in that interval. So if I go back to my y prime equals 6x minus 12, and I put 0 in for x, then I'm going to get a negative value. is going to be negative 12. I don't really care about the negative 12 part. What I care about is the negative. The sign is going to be negative. It'll be negative 12, and it's fine to solve it down for the number if it makes you feel better. But the sign, the positive or the negative, that's the piece we're really interested in. So I know that the first derivative is going to have a negative sign in the interval from negative infinity to 2. Now you can pick as many values as you want to check in that interval, but any value in that interval is going to have the same sign. For example, if we had said instead of 0, let's say we picked x being 1. 1 is also in that interval, so let's say that we picked 1. So if we said x is 1, then we would have had y prime is equal to 6 times 1 minus 12. Well, it's going to give us negative 6 this time, but it is still negative. And that is the piece that we were more so concerned with, that negative. So we know the sign is going to be negative for every number between negative infinity and 2 in this case. Well, when something is negative, that means it is decreasing for the first derivative. So this is going down like this. Let's see what's happening between 2 and infinity. So pick a number. It doesn't really matter what number you pick, just pick a number. I'm going to pick 3. You can pick anything you want, so pick something that isn't too crazy to try to work with and solve. So if I pick 3 and I do the same thing, I put 3 back in where I see the x in the derivative equation. We're looking for the sign of the derivative, so we're putting it back into the derivative. Well, 6 times 3, that gives us 18. So 18 minus 12, that's going to give us 6. We don't really care about the 6. We care that it's positive. So the positive right here, that's the piece we're concerned with. And that tells us the sign of the derivative in the interval from 2 through infinity is going to be positive. If the derivative is positive, that means the function is going to be increasing. So if you think about something that is going down until you get to 2, and then it's going up, it looks like 2 is going to be a minimum. So we found our critical number, and we found that 2 is going to be the minimum. If we want to find the coordinate for 2, we can do that as well by putting 2 back into our original equation. I'm not checking the sign. I'm not checking if it's positive or negative. I'm looking for the coordinate. So that would go back into our original equation. So we have 3 times 2 squared minus 12 times 2 plus 4. And if we figure that out, we'll have y equals 2 squared is 4 times 3 is 12. 12 times 2 is 24 plus 4. So it looks like when we figure all that out, we get negative 8. So the coordinate then becomes 2, negative 8. And because it is going down and then it is going up, see how that looks like the minimum? So we're going to have a minimum. So what we figured out is that we have a minimum. Now it's called a local minimum because it is only within this portion of the graph. In this case, it will be an absolute because there's nothing else that we would be able to use as a minimum. So, and remember, if it's an absolute, it's also a local. So this is going to be our minimum value on the interval from negative infinity to infinity for our equation 3x squared minus 12x plus 4. So let's see if we can try this again for number 3, but this time we're going to find our concavity and our inflection points. So it's a little bit different, but that's okay, we can figure it out. So for number 3, let's see if we can figure this out. Intervals of concavity and inflection points. So that means that we need the second derivative. So the intervals of concavity and the second derivative, inflection points and the second derivative, they all go together. So let's see what we can do here. First things first, we need our derivative. So we have f of x is equal to x to the 4th minus 4x to the 3rd plus 6x squared minus 1. So that means our first derivative is going to look like 4x to the 3rd minus 12x squared plus 12x, which means our second derivative is going to look like 12x squared minus 24x plus 12. We could keep taking the derivative if we wanted, but the second derivative is what we need, so we are just going to stop there. Now when I look at the second derivative, I see a common 12 here. So I'm going to try to clean it up a little bit because anything I can clean up now might help me when I'm trying to solve it later. So I'm going to pull out that 12, makes it x squared minus 2x plus 1. And I notice that x squared minus 2x plus 1 is a perfect square. That's x minus 1 times x minus 1, which we can rewrite as x minus 1 quantity squared. There we go. We found our second derivative. So now what we need to do is figure out where our second derivative is going to be equal to 0. Well, I already factored it, so our second derivative is equal to 0. We can divide both sides by 12. And we have what's called a double root, meaning we have two roots, but they're the same thing. And we would find that by saying x minus 1 equals 0, so x is equal to 1. So our second derivative is going to be 0 when x is equal to 1. Now we're only checking the concavity here. If we wanted to check for intervals of increasing and decreasing, and we wanted to find those critical numbers, that's when we would have put our 0 into our first derivative and figured out where our first derivative is equal to 0. But that's not what we're asked for. Here we're asked for the intervals of concavity and the inflection points, so that's why we're using our second derivative. So let's see what we can figure out from this one. So let's do like we had above. Let's make a little table and see if we can break it into different intervals. So I'll make a row for interval. I only have 1, 0, so just like we had above, we're only going to have two intervals. So we'll have our first interval from negative infinity to 1. 1 was our 0. So we'll switch our second interval to 1 to infinity. So now we need to know the sign of our second derivative. So f double prime. And we need to know the concavity. There we go. So let's see if we can figure these out. We are looking for our concavity from negative infinity to 1. So pick a number in that interval. Pick a number between negative infinity and 1, and we're going to test it in our second derivative. So between negative infinity and 1, 0 is in that interval, so I'm going to pick 0. So if we say x is equal to 0, then in our second derivative, our f double prime of 0 is going to look like 12 times 0 minus 1 quantity squared. So if we're looking for f double prime of 0, that means that we're taking our second derivative equation right here, and we're putting 0 in where we see the x. So if we do that, we don't care about the value. It's going to be 12 right here times a negative squared is a positive. It'll be positive 1, it'll be positive 12. If you want the number, great. If you don't want the number, that's okay too. What matters more is the sign. As long as we have the sign, we're okay. I'll put the 1 in here. It would be 0 minus 1 is negative 1. Negative 1 squared is 1. 1 times 12 gives us 12. That is positive. So that means that it is concaved up. All right, let's try the next one. So our next one is from 1 to infinity. So if I pick a value between 1 and infinity, I'm just going to pick 2. So when x equals 2. So that means that our second derivative of 2 is going to look like 12 times 2 minus 1 squared. Well, 2 minus 1 is going to be 1. So that means it'll be left with 12 times 1 squared is 1. So we get 12 again. It doesn't matter that it's also 12. What matters is it's a positive. It's okay that they're both positive. In this case, they're both positive. So also concaved up. So what we found here is our intervals of concavity. It's concaved up everywhere. There's no change in concavity. Yes, there's something that's happening. So maybe it is concave up and then maybe it's not concaved up as much, or maybe the concavity is greater, maybe it's less. We don't know that yet. But what we do know is that this graph is concaved up over the whole interval, that there's no change in concavity. So there are our first three questions that we are looking at with our derivatives and the shapes of curves.